right. Oh boy. Welcome. Finally made it. Ah, so many technical difficulties. Never update your software right before you're about to stream. I break that rule sometimes. Usually turns out okay, but sometimes it really doesn't. Okay, so we're back. Welcome. Thanks for joining me. Nice to see you. If this is your first time tuning in, I'm Agent Ultra. We're going to be a little bit shorter stream than usual tonight, because I usually start these about a half hour ago. But we're not today. And on the stream, I usually build stuff in functional programming languages, like Haskell mostly. We build fun little projects. For the past little while, we've been working on wave function collapse. This has been a slightly challenging one. We went off on a diversion for the last little while to try and implement the propagation and elimination step on our own to see if we can kind of figure it out. Kind of got to the end of it, thought it might work, but it's turning out it's not working so well. And we're going back and kind of comparing to a version where somebody has figured it out in a tutorial and kind of showed their own tutorial. And comparing results there and trying to learn how they did it and try to understand the process they came up with it so we can better understand the algorithm. It's kind of one of the more difficult to understand or explain parts. It's probably the part that I've been most confused by. So hopefully we can figure that one out by checking out their algorithm and trying to understand what's going on from their implementation so we can get it working. That kind of thing. So yeah, let's get the code going. Bang, bang. Here we go. Let's go to our main file. There we go. Okay. So, my idea for this was that we essentially look at when we collapse a cell, we have to initialize a stack of removals we want to do. Okay. And the idea here that I was trying to do was, well, let's go. When we collapse that, well, we're changing it up now. We're getting impossible patterns and all this other stuff in the beginning. But anyways, the original idea was that you collapse the cell, and then you go in for each of the directions from the collapsed cell. You go to each of the neighbors, and you say, okay, which ones are which ones can I not place here, based on the neighbor now that's like in the direction for me, and I think that one wasn't, well, it's appeared not to be working because we were getting like an infinite loop. So we'd put each of the ones we wanted to remove on the stack that we found in that neighbor, and then from that neighbor we would go out and find its neighbors based on and so on and so forth, and we were just getting like an infinite stack. It just wasn't finishing. And I was trying to work this out on paper, and I think it's still a viable approach, but I found some edge cases to it. So I'm curious now about following along with the grid bugs tutorial and see if we can just translate this to Haskell in order to better understand why this approach in particular worked well for them. And see if we can get it to work in Haskell. So the idea with this one is that they maintain a data structure for each of the neighbor cells, and the ones that are enabled by it. Let's see if we can find here. Counting enablers. Alright, so this is like, we need a way of telling whether a remove tile was the potential final enabler for any potential tiles in the neighboring cells. And so we'll maintain a count of enablers for each cell, for each potential tile, for each direction. Alright, so tables of tables and stuff here, right? So a tile enabler count is a structure that will be created and kept in a cell. All right, so we have to initialize it, and then basically we update this, it looks like, right? So we initialize it. Initially, every tile in every direction is, at least by the rules, is allowed. I'm not, maybe this is a Rust thing where like we have to give a binding for this name even though we don't use it in here anywhere. Alright, so we initialize that, right? And then the idea is during propagation, while there are some removals in the stack to remove, for all directions of the iteration, we go and propagate the effect of the neighbor in each direction. So enable coordinate, removal, update coordinate neighbor. Neighbor cell, we get the cell. Oh, so we get the coordinate of the neighbor tile based on the one we're at, And for a compatible tile in the adjacency rules, the removal tile, update index and direction. We get the opposite direction. I think maybe in my algorithm this might have not been quite right, but yeah, you gotta get the opposite direction. Look up the count of enablers for this tile. I think this is where we go to the tile enabler counts. We're about to decrement this to 0. And then if there is a 0 count in any other direction, the potential tile has already been removed. And I want to avoid removing it again. Check for contradiction. So apparently we would maybe just throw an exception here or something. This is where you could probably do some backtracking or something if you wanted, if you could reverse all the things you've done so far and get to a good state and then try a different choice. And then we update the stack here. We push it there. So I guess only if only if there are no 0 counts. And then we enable the counts bi-direction direction. There's a lot of mutation going on in here. Which is fine, but it's all contained, which is good. And that's it, I guess. Yeah. Okay, so that's pretty much it seems like. So again, I'm still trying to understand the difference between my approach and this approach. Well, I think one thing is that, like, this mutating this data structure and keeping these counts might be more efficient than what I was going at, which was going to be going through all of the available potential cells and kind of knocking things out. Yeah. Anyways, so let's try and continue on with figuring this out and implementing this and see if we can get it to work and get our test pass with it. Yeah? Yeah. Okay. I think we have enabler counts. Right, we enable account. Right, for each direction, enable it to 0. I think we actually want a decrement direction, it looked like. Looks like we only decrement. Up. Okay, and sort of to make a cell pattern enabler account, we take the pattern results and adjacent rules. We get a pattern enabler account. Okay, so one of those. This is probably the initialization thing, yeah. Counts by direction. Take the adjacency rules, the pattern result. So we get the hold over this list comprehension here is what we're doing. This list comprehension is going to generate the pairs of pattern indexes and directions. So if I went D here, or P is say 0, and my max pattern index is, I don't know, 6. D is going to be all the available directions. What do we have? Yeah. Not going to load that one? Yeah. Okay, it's not going to load. Well, let's say we had directions up, down, left, right. Alright, we get 0 up, 0 down, 0 left, 0 right, 1 up, 1 down, 1 left, 1 right, 2 up, 2 down, 2 left, 2 right, so on and so forth. Right? Makes sense. Okay, so that's what that's going to be. We fold over that with the initialized pattern enable account, which is going to be the basic one. This 1021, where everything starts at 0. And if enabled by the adjacency rules, we're gonna do this. So what is if enabled rules? We just pass in the adjacency rules. It's our first parameter. We get our accumulator, which is the pattern enabler count. Then we get this pair, a pattern index and direction. And so for each PX and direction combination that we had there, like 0 up, down, left, right, 1 up, down, left, right, so on. We fold over those by the compatible or rules in PX direction. So that's compatible tiles here, roughly, or that tile in that direction, that tile index in that direction, by the adjacency rules. So we're going to increment the counts by direction. Oh, so we do need an increment and a decrement. Alright, so we need the increment directions. We, for all the compatible rules, on those counts, we increment the direction there. But we've got a couple places here to fix up some type errors, so let's jump over there. Okay. Those are all good. Let's just run our test runner. Pass. Watch. I think when I was working this out on paper, I just kind of jump over to that, and because I think I understand a little bit more about why we're counting the enabler counts here, not just as an efficiency thing, but also kind of, I think it kind of might allow us to skip some edge cases. So if I draw out my grid, I'm going to make it kind of a big one. Right, and let's say we have 1, 2, 3, and 4 as possible values. Right, so all of these cells have all the potential values so far. 1, 2, 3, and 4, so on and so forth. 3, 4. Oh, well, I wouldn't give to have a Wacom and tablet again. Mouse drawing, super great. Okay, we have a bunch of rules for which ones we need to eliminate. So in my algorithm, let's say I picked 2 here. The idea was that we'd be going to each direction here, and looking at which, say we go to this square up here at the top, this one up here, right? We would check, okay, which ones are allowed to be above 2 here, or up from 2. Right, just one allowed in the rule. We go to the rules map. We say for everything that's allowed to be up of 2, which ones are there? And we'd look at the kind of left side of the rule. And let's say 1 is allowed to be up, so we'd say that one's okay, and we eliminate the rest of them because they're not allowed to be up from 2. Right. And then, well, the idea is we'd be pushing this elimination, I guess, onto the stack. And this elimination, this elimination, this elimination. And so forth. But there is kind of a weird edge case here, where we could have a rule that if we had 2 potentials in here, let's say there was like 1, let me go back up a little bit here. Let's say there was 1 as a potential in this cell and 2 here. Now, we have to check, say, this cell over here on the left. For each of these potentials, which ones are allowed to be right of 1 and which ones are allowed to be right of 2. Now, if we go to the rules map, and there are no rules that allow a particular number in this cell to be right of 1. All right. So 3 can't be to the right of 1, 4 can't be to the right of 1, 1 can't be to the right of 1, and 2 can't be to the right of 1. We don't necessarily need to eliminate any of these because we still have another number to check. Right? But that also means that we can't pick one as a value here. See what I mean? So we'd kind of have to like have this case where we'd have to like, okay, well, when I check 1 for this neighboring cell and nothing, there's nothing here that can be to the right of 1, we have to like go back to this cell and eliminate 1. Right? And then there's the case of like, well, if 1 is the only potential thing, we can't do that, then we have a contradiction because now we've eliminated the last potential from this cell that we're checking, and yet all these kinds of edge cases. Whereas, I think with this algorithm, where we count the enablers in the directions, we just have, yes, we have to like do all this bookkeeping about updating the counts as we go along, but we only have 1 check for contradiction here. Right, so it's not like this, okay, I'm looking at this cell and I'm checking this potential tile, and then the neighbors, eliminating all the potential neighbors in that one, and then, oh, if I didn't find any neighbors that are enabled here, then I've got to eliminate this potential, and then that could cause problems. Right. We just have this 1 here. I think that might be the primary difference here. Ooh, spelling mistake. But yeah. So let's continue on down this route and see. This might be the way to do it, right? It seems like a pretty good path. If they've got this working, we can make it work too, right? We just got to translate it into Haskell. So that's kind of an interesting, that's kind of the thing, like that might be the way. Yeah. Anyway, I'm gonna stop doing that and let's just go into, let's go back into the code here. Okay, so let's make it the cell pattern enabler count. Okay. So we have to implement compatible now. In order to do this, we get the adjacency rules, a pattern index, and a direction, and we have to return the list of pattern indices that are compatible with this pattern index. And I think the way this goes, I don't know why we're ignoring tile B here and how this is supposed to work, actually. I don't know if they specify the definition of this function anywhere. It's kind of just used. Well, from this comment, it says it should be all the tiles which may appear in the cell, 1 space in direction from a cell containing tile A. So, our rules are like pattern 1 is allowed to be right of pattern 2, say. All tiles which may appear in the cell, 1 space in direction, from a cell containing tile A. So which one of these is tile A? In direction. For a given cell with a tile index A, file A, in direction B, this cell tile enabler counts of A, bidirection of B, is the number of different tile indices permitted in the immediate neighbor cell in direction B. Adjacent to tile A in our direction B. So I'm going to assert, or just try, asserting that 1 here in our example is tile A. That they mean this is tile A. And that these two together means like one in direction right, this one is tile B, what we're looking for. So we're looking for the set of these. Right, so 1Rs, all the 1Rs, and then we want to get the values of the Bs out here into our list. And then for each of those, we're going to update counts by direction. +1, and we're going to put that into an array, or a vector. And we're going to fold that into our enabler counts. Actually, this initializer is returning a vector of tile enabler counts. Okay. So let's adjust our types here. So our pattern enabler count. We need our adjacency rules. We get our pattern results so we know the number, the map enabler count, adjacency rules. And we should get, say, a list of pattern enabler counts. This is no longer needed for. Let's get rid of that. Okay. Get the tile indices for all the tile indices. We want to get an initial tile enabler count for each direction in the compatible tiles. We're going to update that thing and collect those results together into our output list. So it's almost like we want to do something here for each index, each pattern index in 0 to maximum pattern results. Index. Okay. what we want to do is we want to initialize the tile enable account and add that. Pattern, enabler, and key. Our init pattern enabler count is pattern index and to pattern enabler count. Right? At least the types line up. We haven't used the adjacency rules yet, so we need to use those. Pass them in there. I think we also could have them in scope here. The body of the square clause. Put a hole there. Not telling me what's the scope. But it is down here. So the adjacency rules is in scope for that hole. Okay, so what we want to do there is essentially, I guess we can fold over a list of compatible tiles. And we'll give the tile enabler count, a new tile enabler count as our initial accumulator, and then we update our accumulator with count stop by direction, direction +1. And that will collect together into our list. Pattern enable account and the input list is going to be the compatible tiles every direction. Just yet. Yeah, so that function is going to be pattern index to data back. So I'll pull everything in yet. So we should figure out what this hole is, I think. Which it really is compatible tiles in all directions. So if we concat map list of compatible tiles, give the adjacency rules, and tile A, that will be our pattern input pattern index. Fix. And this will be directions. And we just have this hole left. Which gives us the nice little shape of pattern enabler to pattern index, pattern enabler count. I think that feels right. Stick that in there. I think everyone will be happy. Sort of. Tests aren't going to be happy. Yeah, we know those aren't good, but everything else it's building. Okay, except for undefined here. So this increment enabler counts function here. It doesn't have to mention tile B. We just have to increment it by the direction plus 1. So this compatible function here, we need direction in scope. Which this isn't going to fit. Oh no, okay, we are good. So let's get the whole. All this enable accounts. We have the pattern X in the direction B. Actually just need direction. Okay, so we're just mutating that. I guess the idea of this return vector is that this is going to be indexed by the tile index, so the pattern index. index A, so the A side of the relationship there. Looks like. Okay. So in that case, we would actually increment direction. We don't need anything regarding the pattern index itself. So let's remove that. Type should be just direction. So compatible. Just returns the list of direction. And in order to do this, we just need increment direction, enable accounts. Looks like we flipped the arguments around for some reason. Oh, I'm gonna flip them the other way. Just so that fits nicer. Yeah, just to be consistent with decrement, we'll just go ahead and do that there too. Why not? That. There. There. Right, and then we end up just doing that, which means we could just replace this whole thing. Just increment direction. Get rid of this. Okay, so as long as we can move them compatible, that should all fit together. Get rules, get the pattern, fix, direction. Yeah, we get direction from here. Here. This is really just acting kind of like a... What is this? Acting like a filter. For each of the directions here. If we get the compatible pattern index and direction. What does that even mean? That's what's confusing me about this code right here. Is that we're ignoring this. Meh. This doesn't make a whole lot of sense to me at the moment now. Okay, so what we want here really is to get the... We just want to mutate counts. This is okay, procedural code. Counts for each direction, such that we're only looking at the compatible tiles in that direction. Like if I was to do this faithfully, pattern index. You get a list of pattern indexes back. Right. If I'm just going to focus on this expression here. Right. That's essentially what we're doing. We're creating a compatible list. Adjacency rules is going to be our implicit first argument. Tile A, that's our pattern index. Direction, and then we get back a new list, right, of pattern indexes. Okay, so now that we have that established, let's just focus on this. So, adjacency rules is a map. And we can do something with those. We can convert it to a list of values. And then we have the whole... This is the whole is our list of tuple A0, A0 to list of pattern index. To list. So, our adjacency rules, I actually have to get the... Get adjacency rules. That's better, which makes this whole adjacency key bool to pattern index. So we only want the ones that are true. One items over here. So now we have only the ones that are true, and we still have to use our pattern index and our direction. So we need another filter again on the adjacency keys here. So after we do the first, the adjacency key here, the bool, this is where we want to use our pattern index and direction. So I think if we go back to our definition of adjacency key, pattern A, part, and direction. Where pattern adjacency key is where pattern A equals A and direction equals direction. A equals pattern X and D is equal to direction. Put the whole thing in some parentheses here probably. It's kind of ugly, but let's just keep going here. So now we have that filtered down, and now we just want the adjacency keys and we want the pattern B out of the adjacency keys. We want something after taking the first element, that pair, and we want the pattern B of that. So now this expression no longer works. And it doesn't work because increment and direction, we're expecting directions, but we're returning pattern indices here. Right. And this code, that can be done. So we kind of have these sorts of loops that like do this stuff where we kind of ignore tile B. Here we still have this outer scope of directions here. So we're mutating counts on. And mutating ret. Pushing counts onto it. We don't quite have the same thing here because our loops are not nested in that way. What if Excuse me for a second. I dropped my mouse again. Alright. Where was I? What if... we pass in the pattern directions in our list comprehension? Would that be the same thing? Would that mean the same thing? Right? And then when we enable the init pattern enabler count for each direction, this is going to be for each tile, for each direction. So we're basically just lifting direction up into here, up into this iteration. If we could do that in the Rust code, make it mean the same thing. And init pattern enabler count now would be, this block here would be moved inward. This one we moved out here. So we would be able to do the fold over the compatible tiles, updating the counts. Direction. But we're basically completely ignoring that tile B there in the fold, actually. Which might look a little weird. So this would be compatible. Adjacency rules, yeah, that's in scope. Our pattern index and our direction. And this here, we have to ignore its argument and increment direction dir. And then, we'd have to give the... what's the type of that thing again? Oh yeah, we have our accumulator first. Yeah, we ignore the incoming argument, the tile B, so to speak, and we just increment the increment direction dir. We gotta give the counts first. Right? Okay, so for each compatible adjacency rule there, we just update the counts, collect all those together to make our enabler count. Okay. Fuel. So then we have to do this, use this function for each, okay, so we're initialize each of the cells when we're creating this wave state. here. And then we go make all pattern enabler count. We have to pass in the adjacency rules. Pattern results. Find that here as P. Adjacency rules. Oh, we need the adjacency rules. We build those. I think we can build those from here. The list of pattern A's, get the adjacency rules. Kind of expensive to compute, I suppose. Sort of. Maybe not really. Some folds. Make cell. And not grid. We get the frequency ins here. Adjacency rules. No. Generate those here. We might have to thread those through in order to make that work. Apply that there. There, there. Adjacency rules. Put that there. That there. Okay. Check with chat. What's going on, chat? Gotta bring those in the scope. Here. And we're gonna pass those through here. Mux cell. And we need those here. Here. Bring them in the scope. And then we put them here. Fill that all. Okay, so we wanted, oh, okay, the cell enabler counts needs to be a list of text pattern a That's what those are. Okay, so that's done. Now we propagate. So for each potential tile that was removed from a cell, propagation will visit each neighbor of that cell and update their enabler counts. This relies on the fact that for a given tile permitted in a cell, all compatible potential tiles in a neighboring cell. This stuff is it's so confusing to explain this in English. Right? This relies on the fact that for a given tile permitted in a cell, all compatible potential tiles in a neighboring cell will be contributing to this tile's enabler count in the appropriate direction. So everything that is, if we have 3 in our cell, the one to our left will be all the things that allow right of 3, something right of 3, or something left of 3, something to be left of 3. Right. All of those rules are the compatible potential tiles. Right, so of the potential ones that can be picked in that neighboring cell, which ones are allowed to be left of 3. Those contribute to 3's enabler count. Right, so if there are 2 potential tiles in that set, then 3's enabler count should be 2. But removing potential compatible tiles, therefore, reduces the enabler count, right? So if I remove the ones in the neighbor cell and remove one of them, then 3's enabler count needs to be updated. If that makes sense. Okay, so we pop off our removal to update. Okay. Okay, so relative. So this is all fine and dandy. So for each, we pop off the removal, and then we check for each direction. We get the neighbor cell, and then for the compatible tiles, using compatible tiles function, where we have to remove a tile, update, so the index off of the tile we want to remove, and the direction. Figure out what the opposite direction of is of the one we're currently looking at. And then that is the enabler counts of the neighbor cell. So in our cell we have 3, and we say 3 allowed to be, we use direction to go like the neighbor cell in that direction. That's what this is doing here. And then relative to here, we get the opposite of the direction, and so that means that we're just flipping around. So like if we had right, we would get left. And so that when we look at the rule enabler counts of a rule. Neighbor cell, time account, compatible tile. Bidirection, direction. Where do we use opposite direction? Right, why do we need opposite direction? It's not used again. It's bound for no reason? Now I'm getting a little worried that this code maybe only happens to work, maybe, but maybe has subtle bugs in it. Yeah, so that's not even used again. It's just they create a let binding for no reason. Maybe this was supposed to be removed. Okay, so look up the count of enablers there. So this would be... So, blah, blah. For compatible tile, incompatible tiles of the one we want to remove in the direction. Neighbor cell we figure out from the removal update coordinate neighbor direction. That's just to get the neighbor cell itself. Okay, so yeah, okay, I think I get what's going on here. Alright, so we have our grid here. Right, and say this is the cell we're looking at. Right, we get the removal update. And then for all directions, removal update coordinate to neighbor. Okay. Okay, so the removal update, pop that out, and then for all directions, we look at the removal update's coordinate. So let's say that's pink here. And we get the neighbor in direction. So for each direction. So let's start with like up, say. Okay. I don't know if you can see that. Probably not very good. Yellow's not a great color for this. Okay, so we go up. Up. This way. Yeah. Okay. And then we get this cell here. Okay, that's going to become neighbor cell. Then we iterate all of the tiles which may appear in the cell, one space in direction from the cell. Okay, so we get basically the compatible tiles for direction that we're currently looking at. So we get all of the ones that are compatible with this one we want to remove, pink. In direction. So we're going to be looking for pink up. And then opposite direction makes no sense. We don't even use it again. The enabler counts. for that neighbor cell for that compatible tile. So of these, so we look at the tile enabler counts for this cell, and we're looking for for each of the compatible tiles of the thing that we want to remove, pink. Okay, so all the ones that are pink, that are enabled by pink. If we're about to decrement it to 0, or not. If we are, so there's exactly one. So it's like kind of an edge case here. If there's a 0 count in another direction, the potential tiles are already being removed, and we want to avoid removing it again. Check for contradiction. It doesn't really do anything with it, but then we probably change the cell's entropy, did we? Add the update to the stack. Compatible tile. Decrement. Okay. Interesting. So that goes into all of the enable accounts by direction. Okay. I want to say, I think that kind of makes sense, maybe. I don't know. Okay, well, what's the type error here? Just the spelling thing. Okay, that's all fine. Where we at? Tests all busted because I'm changing types. Have some top level things. No good. Okay, so let's look at propagate then. The thing we want to remove. We have nothing that we're done. While we pop off the stack, there's nothing after the while, so we have nothing, we're done. Otherwise, we have a remove pattern. I think we can get rid of this. Get rid of this. We got a hole here. Okay, so translating this into a more functional approach, that's not impossible. It's a little weird, especially because I think some of this code's be just kind of like copy pasta and not updated properly. So we could do a fold over all the directions. What would we produce? A value out of that. We're only really using this iteration for the side effect of updating some state. Right. So in that case, we could just do foreign, and we throw away the results of directions. Right, then we get this hole here. Okay. So we're good there. So now we have direction in scope. And in this code, they want to get the neighbor coordinate and the in order to get the neighbor cell. We get the neighbor coordinate from the removal update. Get the coordinate, and we calculate. So we have to do some calculation in the direction in order to get the neighbor coordinate, to get the cell. We have this function in order to do that. Okay. And then we do another for each compatible tile. Updating the cell. And get the tile enabled counts, put a compatible tile for that cell, and do this check. And if we get in there, neighbor cell remove tile, mutate that cell. That's where we check contradiction. Then we update the list and push a new removal update, put compatible tile at the neighbor coordinate. And then we finally mutate the cells stuff. So this all block for each of these things updates the cell, does like a modification of the cell in the grid. Right, and updates the states pattern entropy list or whatever for that cell, and also the stack of removal updates. So let's pop over here. So we know we have to what do we want to do? What do we want to do? We want to get the cell first. Cell coordinate from the removal direction. And then we have functions for modifying a cell in the grid, I think, through its state. So hopefully that will all patch together just fine. Let's do that. Okay, so neighbor. We need to do neighbor chord. Neighbor cell would be get cell at. Neighbor chord. Know that this should be which is going to be coordinate. It will in a moment. I'm just going to put the type in there just so that all my other holes have Okay, so get cell at neighbor chord, that's fine. And now, let's see, can we get the enable accounts from that neighbor cell? We check if we're about to do it to 0, and then we do some modifications potentially. Mutating the cell, the neighbor cell, updating the entropy, the heap list, and updating the things. So this is more state stuff, which is fine. Okay, so then let's get the enable accounts. From the neighbor cell. Okay, that's fine. So we have the enable accounts in scope here, all that stuff. And we want to index into that to get by the compatible tile. Alright, we have to do compatible tiles by Jason. Alright, so we have another 4M in here. And 4 get the enable accounts. And that's going to be compatible by the adjacency rules. For I took 2 arguments. Maybe just needs direction. Compatible pattern. So bring adjacency rules into scope. Gets wave state adjacency rules. We want a pattern index. That's the removal update. Remove pattern removal possibility. Propagate cell pattern index. That should fix that. Yes, yes. Okay. Okay. And now we have the enabler counts. And we actually want to index into that based on the compatible pattern. We can do that with, I think data.list has the function. It's not exactly safe, but it should be. Which is famous last words on this journey here. Bang bang. Now, see touch pop. No, thank you. Don't do that. Get a different job, friend. I'm gonna have to ban you. Okay. Alright, so we have the enabled accounts now. That should be just the enabled accounts for the compatible tile. Now we check direction. We do a bunch of things. Otherwise, we do nothing. Contains any zero count. So, when contains zero count, enabler counts. When it's not. We do stuff. And regardless, afterwards we mutate enabler counts for that cell. So I need to check. I think I've got modify cell at. Which turns either string cell, and I guess on the right. And what's that? Yeah, so that's the one we want to use. So enable accounts. So this is enable accounts here is the neighbor cell. So we use neighbor chord for our first argument. And then our function that we want to update it to updates it. That's going to be doing our decrement direction. Updating the field of the cell by using the decrement there. Update cell enabler count. I might be able to do it like this. Updated cell enabler count. see, that would be... This would have to be a cell to either string or cell. Update. Define that later. Okay. The rest of this, let's see. So we modify the cell at the neighbor cell to remove the pattern. Remove cell at also at neighbor chord. And this will be compatible pattern. Yeah. That's going to take pattern index, cell, and return either string cell. Yeah. Okay. And then we have to, well, there's possibility to do something about contradiction. Then we have to update the entropy list, or the entropy list, and add removals and stack. Okay. We have to modify the wave state entropy list. Yeah, how do we do only ever build it once, so we have to update it. We change the cell state there. So actually, we actually have to implement that. Looks like we haven't really done that in code yet. Oh no, wave state entropy. Yeah. Cell entropy list. Oh, sorry, that's fine. We read it. Modify it there. add the entropy cell. We modify it here. Alright, we're gonna have to do that at some point. Where were we? Okay, we're gonna have to leave those as to-dos because I'm running a little over time, but I'm just making up time for the time I lost, starting the stream a little late. So there we go. We have to implement contain 0 still. So I'm gonna go to where we have the enabler count defined roughly. Kind of define it around there. Contains 0. Take pattern and count. To bool. Contains 0 count. That is what I want to name it. Enabling count there. Okay, that's better. This button index cell, action cell. So that's remove pattern. Oh, which is bound up here. Cell. Here. Okay, so that's the neighbor coordinate direction thing. Okay, this is probably a an enough-ish place. We'll create a little work in progress commit here. Updating enable accounts. And push that up. Okay, so first time tuning in, thanks for watching. You know what to do. If you're subscribed here and you're a Twitch user, you know, give us a follow, set up your notifications, you'll get notified when I go live. Super simple. If you're watching on YouTube, because you're in a different time zone or because you're catching up or whatever, I don't judge. I like everybody on both platforms. Anyways, if you're on YouTube, you know what to do there. Like, subscribe, thumbs up, comments, whatever. All good. All my links, all the code you've seen here tonight, actually, is on GitHub. I'm Agent Ultra on GitHub in most places, not all, but definitely there. It's wave function collapse. Okay. You get the code there. You can find me on Mastodon at types.pl. I'm Agent Ultra there as well. And on there, you have the links to everything else. My website, Twitch, YouTube, all that stuff. Cool. Let's see. If you go to the link above me, that is goes to declarative.tv, website where you can find streamers who do programming in other declarative style languages like Haskell, but others as well. And on that site, there's also a link to our Discord server where you can find this channel for this stream and for all the others as well. And then, yeah, if you're watching on YouTube or you have something you want to chat about between streams, can find me there. And follow me on the socials. That's usually where on Mastodon, where I post about this stream and upcoming things, things I'm thinking about. I put polls up every now and again for kind of content you want to see and see me work on and all that stuff. So that's all I got for now. Thanks for tuning in. See you. I usually do these streams on Tuesdays, so might see you next week. Of the last week of August, I will be on vacation, so I'll be out for that one. And yeah, so happy hacking out there. May your monads always be free, and your types always check. And see you next time.